Hi everyone, so today's lesson is going to be regarding chapter 6, which is all about understanding organic chemical reactions. So here's a brief outline that basically summarizes what this chapter is all about. So we're going to take a look at the general types of organic chemical reactions. We're going to look at bond breaking, bond forming, the difference between homolytic cleavage versus heterolytic cleavage, and then we're also going to look at bond dissociation energy and how that's related to bond length. And you already have a general idea of what that's like based on what you learned in general chemistry. And we're also going to take a look at thermodynamics, energy diagrams, and kinetics. And so we're going to compare a fast chemical reaction versus a slow chemical reaction, rate law, transition state, activation energy, and all those things related to thermodynamics in general. So in a lot of organic chemical reactions, we always begin by searching for electron-rich sites. And these electron-rich sites are the functional groups. Remember, the functional groups are the reactive sites. These functional groups are considered reactive because they contain heteroatoms that are surrounded by lone pairs of electrons. And these lone pairs of electrons can participate in organic chemical reactions. We also search for electron-deficient sites. So for example, carbons and hydrogens that are bonded to these heteroatoms are considered electron-deficient sites. We also try to locate bonds, double bonds and triple bonds, because they contain pi bonds that can also participate in a lot of chemical reactions. You're also going to learn how chemical reaction takes place. For example, does it happen in a single step or in a series of steps? In general chemistry, you learn that the slowest step is the rate determining step, and that you can write a rate law equation based on the rate determining step. And so we're going to take a quick trip down memory lane and talk about kinetics one more time. So what does an organic chemical reaction equation look like? Well, it's basically like any other chemical reaction equation that you've seen in general chemistry. You have the starting materials or the reactants on the left-hand side of the arrow, and then you have the products on the right-hand side of the arrow. Equations for organic reactions are usually drawn with a single reaction arrow. And the reason behind this is because you want that chemical reaction to move forward and not backwards. So you basically want that chemical reaction to favor the formation of the products. You can also include reaction parameters in the reaction equations. You can include reagents above or below the arrow. So for example, here we have bromine gas as a reagent reacting with cyclohexane to form bromocyclohexane. You can also include other reaction parameters like light, which is indicated by the symbol Hν, or delta, which indicates that heat was added. You can also include parameters like the solvent that you use, such as CCl4 or tetrachloromethane. So here's a few different ways of writing organic chemical reactions. You can see here we have cyclohexene reacting with bromine gas to form 1,2-dibromocyclohexane. Here we have the bromine gas written on the reactant side along with cyclohexene, or you can also write it right above the arrow. These two chemical reaction equations are one and the same. You can also include other parameters like heat, light, or solvent, or even temperature in the chemical reaction equation. And when you have two sequential reactions, the steps are usually numbered above or below the reaction arrow. So for example, the first step here indicates the first chemical reaction, and then the second step indicates the second chemical reaction. So here we have acetone reacting with methyl magnesium bromide first, followed by the chemical reaction with water to form alcohol. So the inorganic byproduct is usually omitted in the chemical reaction equation unless that byproduct is used again in another chemical reaction. So there are three general types of organic chemical reactions that you're going to learn in this chapter. There's substitution reaction, elimination reaction, and addition reaction. Substitution reaction is a reaction in which an atom or a group of atoms is replaced by another atom or a group of atoms. Here's an example. So let's say that we have this atom Z that's bonded to a carbon atom. Z can be either a hydrogen or a heteroatom. And then we also have an atom Y. So in a substitution reaction, Y replaces Z. So now you have Y that's bonded to a carbon atom and Z by itself. So this is kind of similar to single displacement reaction that you learn in general chemistry, except single displacement reaction involves ionic compound and metals. And substitution reactions are specifically for organic chemical reactions. Substitution reactions involve sigma bonds. One sigma bond breaks and another sigma bond forms at the same exact carbon atom. So here we have an example. We have a carbon to iodine sigma bond, and this chloride ion will take the place of this iodine atom. So now you have a carbon-chlorine sigma bond. So one sigma bond breaks and another sigma bond forms. The most common examples of substitution reactions actually occur when Z is a heteroatom rather than a hydrogen atom. And the reason behind this is because heteroatoms are typically more electronegative than carbon. Here's an example. We have a chlorine atom that's bonded to a carbon, and this carbon is double bonded to an oxygen atom. So it makes this carbon atom extremely electron deficient. And so this hydroxide ion can donate some of its lone pairs of electrons to this carbon atom, which then results in the cleavage of this bond between carbon and chlorine. Right? So it breaks this sigma bond between the carbon and the chlorine atom, and then what forms is the carbon to oxygen bond coming from the hydroxide ion. Right? And then you have the chloride ion as the leaving group. The second type of organic chemical reaction is the elimination reaction. And elimination reaction is a reaction in which elements or atoms of the starting material are lost and a pi bond is formed as a result. So here's an example. We have this compound right here containing X and Y, and X and Y can be a hydrogen or a heteroatom. And then when you react this via elimination reaction, then the X and Y atoms will be lost. They will be eliminated, and a pi bond is formed as a result. So the two atoms are usually bonded to two adjacent carbon atoms. So again, in elimination reactions, you have two groups, X and Y, that are removed from a starting material. So because we're removing two groups of atoms, two bonds are being broken, two sigma bonds. And as a result, a pi bond is formed between two adjacent carbon atoms. So the most common examples of elimination reaction actually occur when one of the groups of atoms is a hydrogen and the other is a heteroatom. Here's a few examples. So here we have an ethyl bromide that's reacting with a hydroxide ion, which is a very strong base. And so here in this elimination process, you can see that the hydrogen and the bromine atoms get cleaved off of their sigma bonds. And so as a result, a new pi bond is formed between the two adjacent carbon atoms. So this is a general pattern that's observed in a lot of elimination reactions. And here's another example. We have cyclohexanol, which is reacting with a very strong acid, sulfuric acid. So in this elimination process, the hydroxy group and the hydrogen get cleaved off of their sigma bonds, and as a result, a new pi bond is formed between the two adjacent carbon atoms. And the third type of organic chemical reactions are the addition reactions. And an addition reaction is a reaction in which elements are added to the starting material. So this is the exact opposite of elimination reaction. You can see that in addition reactions, a pi bond is broken, right? So a pi bond is broken between these two adjacent carbon atoms, and two sigma bonds are formed in these two adjacent carbon atoms. So here's a few examples of addition reactions. So the first one here involves the reaction between ethylene and hydrobromic acid, which is a stronger acid than hydrochloric acid. So here a pi bond is broken between these two adjacent carbon atoms, and then this results in the formation of sigma bonds in these two adjacent carbon atoms. So a carbon to hydrogen sigma bond is formed, and a carbon to bromine bond is also formed. And here's another example of an addition reaction involving cyclohexene. reacting with water in the presence of a small amount of sulfuric acid. And what we get is a cyclohexanol. And in this addition reaction, this pi bond between these two adjacent carbon atoms gets cleaved and results in the formation of two sigma bonds. So a carbon to oxygen sigma bond as well as a carbon to hydrogen sigma bond. So this is the general pattern observed in a lot of addition reactions. And as I've mentioned earlier, addition and elimination reactions are the exact opposite. A pi bond is formed in elimination reactions, whereas a pi bond is broken in addition reactions. And these two reactions are actually reversible. So you can use elimination reaction to form a pi bond, or you can use addition reaction to break the pi bond and form the sigma bonds. So here's another example of an organic chemical reaction. So we have molecule X reacting with molecule Y to form capsaicin and hydrochloric acid as a byproduct. So of all the three types of organic chemical reactions that we looked at, which type do you think this is? So let's analyze the types of bonds involved here in this chemical reaction. So you can see that we have a carbon to chlorine sigma bond that's broken and a nitrogen to hydrogen bond that's also broken. And so when you look at the product side here, you have a hydrogen to chlorine sigma bond that's formed and a carbon to nitrogen sigma bond that's also formed. So in other words, we have two sigma bonds broken in the starting materials and two sigma bonds formed in the products. And so as you can see, no pi bonds are involved in this chemical reaction. No pi bond is formed nor broken. And so this must be a substitution type of reaction. Here's a practice problem. Classify each transformation as substitution, elimination, or addition. So for the first one here, we have a carbon to oxygen sigma bond. And then in the product side, we have a carbon to bromine sigma bond. So you can see that the carbon to oxygen sigma bond was broken, and then the carbon to bromine sigma bond was formed. And so this is an example of substitution reaction. And for the second chemical reaction here, we have a carbonyl group versus a hydroxy group. So you can see that there's a pi bond present in this carbon to oxygen double bond, but no pi bond present in this carbon to oxygen bond. However, there is a oxygen to hydrogen sigma bond as well as a carbon to hydrogen sigma bond. So a pi bond is broken and two sigma bonds are formed. So this is a perfect example of addition reaction. And for the third chemical reaction equation here, we have a carbon to hydrogen sigma bond and a carbon to chlorine sigma bond. So that means that the carbon to hydrogen sigma bond was broken and then the carbon to chlorine bond was formed. So this is a simple example of substitution reaction. And for the fourth chemical reaction equation, we have a carbon to carbon single bond and a carbon to carbon double bond. So that means there's a pi bond that's formed here. And so that means that two sigma bonds must have been broken. So we have two hydrogens here. And then now we only have one hydrogen left. So that means that one of the carbon to hydrogen sigma bonds was cleaved and the carbon to oxygen bond was cleaved as well. So two sigma bonds broken and one pi bond formed. So this is a perfect example of elimination reaction. Here's practice problem number 2. Classify the conversion of A to B as a substitution, elimination, or addition. B can be converted to the female sex hormone estrone in 2 steps. So the first thing that you should do here is to analyze the difference between molecules A and B. So you can see that in molecule A, there's a double bond here, which means there's a pi bond. And in molecule B, there's only a single bond here, but there is a carbon to chlorine sigma bond as well as a carbon to oxygen sigma bond. So that means that a pi bond was broken and two sigma bonds have formed. So because a pi bond is broken and two sigma bonds are formed, this is a perfect example of addition reaction. So in every organic chemical reaction, there's always a reaction mechanism, which is a detailed description of how bonds are broken and formed as reactant is converted into product. So it basically illustrates how molecule A is converted into molecule B. Some chemical reactions happen in a single step, while some others happen in multiple steps. If a chemical reaction happens in a single step, then it's known as concerted reaction. So it doesn't matter how many bonds are broken or formed, the reactant is always converted directly to a product. The second type of reaction mechanism involves more than a single step, and this is known as a stepwise reaction. In a stepwise reaction, a reactant is converted into a reactive intermediate, which is considered an unstable intermediate that gets converted immediately to the product. So there are two ways to break a bond, either homolytically or heterolytically. So here's a single bond connecting atoms A and B, and you know that a single bond contains two bonding electrons. And so when you break this bond homolytically via homolysis, that means that you're distributing the two electrons evenly or equally among the two atoms involved in this bond. So again, if you have two bonding electrons, you're going to distribute that evenly among the two atoms. So one electron will go towards atom A, and then the other electron will go towards atom B. So this is what it means to break a bond via homolytic cleavage. In order to illustrate the movement of a single electron, we use a half-headed curved arrow, which is also known as a fishhook. So again, in homolytic cleavage or homolysis, a single bond is cleaved, and then the two bonding electrons are distributed equally among the two atoms involved in that bonding. And so one electron goes towards atom B, and then the other electron goes towards atom A, which is shown by this fishhook half-headed curved arrow. So to summarize this, homolysis basically generates two uncharged species with unpaired electrons. And a reactive intermediate with a single unpaired electron is also known as a radical. And radicals are very, very unstable. The second way to break a bond is via heterolysis, which is also known as heterolytic cleavage. In heterolysis, you have two atoms that are bonded together with very different electronegativities. And so when you break this bond via heterolysis, both electrons will move towards the more electronegative atom. Hence, we have unequal distribution of the electrons. So here's an example. Let's say that we have two atoms that are bonded, A and B B, let's say, is a more electronegative atom. And so when you break this bond via heterolysis, then the two bonding electrons will move towards the more electronegative element, which is B. However, if A is the more electronegative atom, then breaking this bond via heterolysis results in the movement of the electrons going towards the more electronegative element, which is A. And because we have unequal distribution of the electrons, you can see that one of the atoms will gain a negative charge, and then the other atom will gain a positive charge. Since two electrons are transferred to the more electronegative atom in heterolysis, a full-headed curved arrow is used in order to show the movement of this pair of electrons. So heterolysis of a carbon to Z bond or a carbon to heteroatom bond generates a carbocation or a carbanion, both of which are charged species. Both carbocation and carbanion are unstable reactive intermediates. The only difference between them is their charge. So a carbocation contains a positively charged carbon atom, whereas a carbanion contains a negatively charged carbon atom. Breaking a carbon to Z bond could result in the formation of 3 different reactive intermediates. If you were to break a bond via homolysis, then this generates a radical reactive intermediate, which means that you have an unpaired electron on the carbon atom. If you were to break a bond via heterolysis, then you can either generate a carbocation or a carbanion. A carbocation has a positive charge on the carbon atom, whereas a carbanion has a negative charge and a lone pair on the carbon atom. Radicals and carbocations are considered electrophiles because of the fact that these 2 carbon atoms here are considered electron deficient. They have an incomplete octet, and so they're considered electrophiles. Carbanions, on the other hand, are considered nucleophiles because they contain a lone pair of electrons. Here's a practice problem. By taking into account electronegativity differences, draw the products formed by heterolysis of the carbon-heteroatom bond in each molecule. Then classify the organic reactive intermediate as either carbocation or carbanion. So looking at this first molecule here, you can see that we have a heteroatom, which is oxygen, and oxygen is more electronegative than this carbon. And so via heterolysis, the 2 bonding electrons will move towards the more electronegative oxygen atom. And so now this leaves this carbon atom a positive charge, which makes it a carbocation. For this second molecule, you can see that bromine is more electronegative than carbon, and so the 2 bonding electrons will move towards bromine. And so this leaves this carbon atom a positive charge. And again, this is a carbocation. And for the third molecule here, you can see that the carbon atom is more electronegative than the lithium atom. And so the 2 electrons will move towards the carbon. And so now we have a negatively charged carbon atom, which makes this a carbanion.